Hello, Math 8 students. This is Utah Middle School Math Project 2.1a on proportional relationships. In this unit, you're going to learn how to write an equation that has two variables to represent a situation. I want you to think way back to earlier in the year. We were writing equations, but they only had one variable, just one x, one unknown. And now we're going to start finding relationships between two variables and writing equations to tie two variables together. We're going to start with something simple, the proportional relationships that we've reviewed or that we studied in 6th and 7th grade. We are very familiar with that, and we're going to make some connections with those proportional relationships and kind of grow into the more complicated relationships of linear equations. So, to get started, we have this situation. Julie is picking teammates for her flag football team, and she picks 3 girls for every boy. So here is the table. Will you start filling in that table? With that information, since it's 3 girls for every boy, if one boy is chosen, then that means Julie is going to choose 3 girls. 2 boys means that Julie will have chosen 6 girls. 4 boys will mean Julie has chosen 12 girls. I'm sure that at this point you notice enough of a pattern, so can you use that pattern? What if Julie chose 9 girls? How many boys would she have chosen for that? Yeah, 3. How did you get that? Tell me what you're doing in your head. What relationship are you observing? Gabe? Yeah. A couple of things that are worth pointing out. So we can see that we are counting by 3s. It's going up by 3 every time. And that is an important observation. We're going to make a connection to that in just a second. But when we're studying proportions, the thing that we love about proportional relationships is that we don't always need to look for patterns going down the table. We can also look for patterns going across the table. How is a 1 changing to a 3? How's a 2 changing to a 6? What's happening there, Dylan? Yeah, we're multiplying by 3. And the reason why that's such an important relationship is because a table is a great way to organize information, but it doesn't always have to be this certain specific pattern. I could decide, you know what, it's a really big team. What if Julie chose 10 boys? Now I can't just add 3 going down the table anymore, right? And so having a way that we can kind of skip some values and still have a reliable pattern is going to be really helpful. So 10 multiplied by 3 is how we get to 30 girls on the team. And then I can also use that relationship in reverse order. It means if I'm going forwards multiplying by 3, when I didn't know this one, I could always work backwards and do the inverse divide by 3. We're going to save this, so don't fill in that one. We're going to save that for just a second. Let's graph that relationship. In order to graph, we need to have a quick conversation. This is an area that students struggle. We need to make sure that we have labels, and we need to make sure that we have a scale. Here's what I mean by that. We're talking about the number of boys and the number of girls. So you might remember that the first column is always going to be what? Grant. Yeah, the x-axis and the x values, which means our second column is going to be the y values or the y-axis. So knowing that this is the x-axis and this is the y-axis, I don't want to just label them x and y. Remember, on the x-axis, we're talking about the number of boys Julie has chosen. So I will also label the x-axis boys, and y-axis refers to the number of girls that Julie has chosen. So we want to include those labels. Yes, Grant? It's just talking about the relationship of how many have been chosen, not necessarily on the team. We don't want to make it complicated. Thank you for clarifying that. That probably could be taken into consideration, but for the ease of this problem, we just want to talk about how many she's chosen. Scaling is the other part that we want to talk about, and scaling refers to what we're counting by. So you can see we've got this grid. What is each mark on the grid going to represent? Think about the situation. Does it make sense to count by halves? No, you can't choose half of a person to be on the team, so it doesn't make sense to scale by halves. Instead, for this situation, it probably makes sense to count by ones. Now I've chosen my scale. I chose my scale when I said that this is a value of 1, but it still is a good idea to continue to label some of them. So 1, One more makes it 2. One more after that would make it 3. But I get to be kind of lazy and things can be kind of cramped. And so I don't always mark and label every single one. I know that this is 3, then I move on, that's 4. I know that that's going to be 5, I move on. And just for space and for laziness, I'm only going to actually put a label on some of those lines. Okay, talk at your tables. What is an appropriate scale to use for the y-axis where I'm counting the number of girls Julie has chosen? Talk with your tables real quick. Ready, set, go. Okay, and thoughts. What are we going to count by? What makes sense here? Leroya. Yeah, 3s make sense. Could I still also count by 1s if I really wanted to? Yeah, I could. Sometimes, depending on our scale, it makes our graph look a little bit differently, and we wouldn't see a whole lot of information if we counted by 1s. And so I do think for this situation, since the numbers are counting by 3s, it definitely makes sense for us to also count by 3s. So the first mark will represent 3, which means the next mark is 3 more than that for 6. 3 more than that for 9, but this is where I start getting lazy and it's getting cramped. So I know that it's 9, but I'm not going to write it. The next one is 12. 3 more is 15. Going to skip it for space. 3 more is 18. 21 and 24. 27 and 30. How am I doing on this so far? All right. And I could keep on going, but I think I'm going to call it good here. Now we can start plotting those points. Over 1 up 3. Over 2 up 6. Over 3 up 9. Notice when I'm going up 9, I'm not counting up 9 of these marks. I'm going to where I know the mark represents 9 girls. Over 4 up 12, and because I also then jumped ahead, I can go over 10 and up 30. Now, I want your attention on the screen one more time. You should notice that this is a nice straight line. And I can draw that line just for the purposes of demonstrating that it is a nice straight line. But it's worth mentioning, because this is going to come up in this unit, it's worth mentioning that when I draw the line, each point on that line has meaning. And that works and makes sense for a point like this one, because it is on the line, and we could have 4 boys and 12 girls. We could have 2 boys and 6 girls, but does this point make sense? What would that actually represent? What would that actually represent, Joshua? Yeah, 2.5 boys and about 7.5 girls. And that's not possible to choose that amount of people to be on the team. And so that is something that is worth mentioning. Sometimes we draw the line because we want to demonstrate that it is a nice straight linear relationship, and that could even go back to the origin, and all of those things are important. But we also want to clarify that in this case, not every point on that line makes sense. I'm only drawing the line just to demonstrate that it's a straight line. Okay. Now we're ready for this. Find the ratio of girls to boys for 7 different ordered pairs in the table. So we've got all of these ordered pairs, these x comma y's, or the boys to the girls, and I want to find the ratio of the girls to the boys in various spots on the table. So I'm just going to go through the table. The number of girls is 3 for 1 boy. The number of boys could be 6 and 2 girls, and so on. And recognize each one of these are equivalent ratios. We're going to write that down. These are equivalent ratios. And you might remember that the definition of a proportional relationship is equivalent ratios. That's why this works out so neatly. Those proportional relationships are defined by being equivalent ratios, and we can see that and observe that here. Okay, one other thing that's worth pointing out. What is the slope of this line? Let's go Gideon. It is 3. a lot of students would look at this and say, oh, well, let's just pick some crosshair points. We're going to go up 1 and over 1. Talk about the mistake that I just made. Why is it not 1? Why is it 3, like Gideon said, instead of 1? Go ahead, Gideon, explain. Yep. Exactly. What Gideon just said, when we're looking at the scale, we're counting by 3s. So when I go up 1 box, I'm not just going up a value of 1, I'm going up a value of 3. And that makes the slope 3 over 1, which simplifies to 3. Isn't that interesting? What's a constant of proportionality? 3. How is it increasing if I'm going up this table? Then can you explain this one? Why am I increasing 18? We're increasing 3 until we're increasing by 18. Can you help me understand that? Talk at your tables. I want to see some more hands, so talk at your tables. All right, and now finish up and come back to me. How is it that I'm counting by 3s until I'm not? What's happening there? Let's go to Gabe. Yeah, 3 can go into 18, but why did it jump to 18 specifically? Grant. Exactly. It all relates back to the slope. The slope is 3 over 1. So yes, eyes on the screen. Voices off. Yes, we're increasing by 3, but why are we increasing by 3? Because this is changing by 1. Rise, which refers to the y values, and the run, which refers to the x values. We're going up 3 every time we're going over 1. So up 3 over 1. Up 3 over 1. Why are we increasing by 18? Because how much am I going over here? 6. And 18 divided by 6 still simplifies to 3 divided by 1. We can observe that here in the table as I jump from 4 all the way over to 10. The rise was 18. The run was 6. Okay, good connections. Wanting to tie in what we have learned about slope so far in our last unit to what we remember about proportions from last year. Here's your challenge now. Can you write an equation? We're going to use a table to help us, and we want to have x represent the number of boys. That's what I saved this last row for. And we're going to have y represent the number of girls. Makes sense. Boys are on the x-axis, girls are on the y-axis. So use that to write an equation. Let's go a 15-second check-in at your tables. What is that equation going to look like? Okay, it got quiet, so let's talk about it. What do you think that equation is going to be? Dylan, give it a try. Yes, exactly. Y equals 3x. And here's a quick reminder in case you're struggling with how that came up. What am I doing with every value here in this first column? We're going forwards across the table by multiplying by 3. So even when I have an x, I'm still going to go forwards across the table by multiplying by 3. And that's how I get that y value. So you can write x times 3 is equal to y. But as we've talked about in many units in the past, we really like it to be y equals. And x times 3 can be rewritten to be 3x. So both of those are great versions of the equation. We can say x times 3 is equal to y, or y equals 3x. And again, making some connections, that 3 keeps on appearing. We're seeing it in the graph, we're seeing it in a couple places in the table, we're seeing it in the equation. Use the equation and the graph to determine how many girls would be on the team if Julie chose 10 boys to be on the team. We've already done this with our table, but let's make some connections again. I'm going to use the graph. 10 boys, so I'm going to follow along on the axis where we're measuring the boys. There's 10. I'm going to trace that up until I land on that graph. Landed there, and then we're going to follow it back over. What is the y value associated with that? That's 30. How am I going to also use the equation? This is just a simple matter of substituting in what we know. So y is equal to 3x, and Julie is choosing 10 boys. That means I know that this x value is 10. And I substitute that in. Y is equal to 3 times x, so y is equal to 3 times 10. Therefore, y, the number of girls that Julie is choosing, is equal to 30. Use the equation then to determine how many boys are on the team if Julie chooses 18 girls. How can I use the equation and the graph? I'm going to start by writing that equation, then I'm going to scroll up to the graph. Talk at your tables. I helped you out with the first one, talk at your tables. How am I going to use the graph in order to figure out this one? Again, Julie is choosing 18 girls. So how many boys did she choose? Talk at your tables. Ready, set, go. Okay, how am I going to use the graph? Let's focus there first. How am I going to use the graph to answer this question? Let's see some hands. Carter? It's not so much about the 3 and the 6. I'm glad that you're recognizing that relationship that 3 and 6 do multiply to be 18. And so we could use that perhaps in the table, but what I want to focus on is if I'm just looking at the graph. Let's pay attention to the information that's given to us. And the information given to us is that Julie chose 18 girls. Where's the information about girls on this graph? Where am I seeing that, Gideon? It's on the y-axis. So what do I know? That it's going to be right here on the y-axis. So when Julie chooses 18 girls, I'm going to follow that over. How many boys has she chosen at that point? 6. And it makes sense making that connection to what Carter already recognized. 6 multiplied by 3 is equal to 18. So we can see that connection. That 3 comes in again because it's the slope. And it's the constant of proportionality. So let's review really quick the difference between those two problems. In the first version, I knew that there was 10 boys, so I went along the axis where we were measuring the boys, found 10, traced that up until I could see the graph, traced it over to find out that the value of girls associated with the value of 10 boys was 30. But now when I switch the information, then we have to work backwards. On the y-axis, I'm measuring girls, so I'm going to start at 18, follow over until I get to the graph, trace it down to see that that is associated with 6 boys. How are you then going to use the equation? We've talked about the graph. How are you going to use the equation? Since I had to work backwards with the graph, what is that going to mean for the equation? Check in with your tables one last time. Okay, and what am I going to do here with using the equation? Let's go, Joshua. Yep. Great. Y is 18. I'm telling you that right here when I'm saying that the girls is 18. So I'm substituting 18 for y, and then I just have to solve the equation. 18 is equal to 3 times x. How do I undo that? We simply divide. Balancing it, doing the same thing to the other side. And that's how I get, as Joshua explained, x is equal to 6. Or in other words, the number of girls is equal to, the number of boys is equal to 6 when Julie chooses 18 girls. Okay, that is a great, very thorough review of proportional relationships. Here's some vocabulary that we need to review as well. So make sure we're highlighting this. In the previous example, the two quantities of interest are in a proportional relationship. Recall that when two quantities are proportionally related, the ratio of each y value to its corresponding x value is constant. That simply means we have equivalent ratios. Those equivalent ratios all simplify to what we call the constant of proportionality, or proportional constant. You might remember from last year we got to be kind of lazy, and so we abbreviated it COP. In that problem, the ratio that related the number of boys to girls was 3. That was the COP for that relationship. Every ratio also has an associated rate. A unit rate is another way of interpreting the ratio's proportional constant. The unit rate and the proportional constant are the same thing, the same number, but how we talk about them is slightly different. So the unit rate, if quantities y and x are in a proportional relationship, which they are here, then the unit rate of y with respect to x is the amount of y that corresponds to 1 unit of x. That's why it's a unit rate, because unit rate, uno, that root word is 1. That means I'm simplifying the ratio of 18 to 6, simplifying that to 3 to 1. And you can see, of course, that 3 to 1 simplifies to 3. This is what we refer to as the COP. And we keep it a rate or a ratio when we still keep the 1. I just answered question 2 in the previous problem. Julie is picking teammates for her flag football team. Express the proportional constant as a unit rate. I just did that. The COP is 3. But what does that really mean? That 3 as a unit rate is 3 to 1. The 3, adding some labels to really make this unit rate have some meaning. 3 refers to the number of girls Julie has chosen, and the 1 refers to the number of boys that Julie has chosen. So 3 girls to 1 boy. Now that we have also reviewed that vocabulary, when you see it come up in the lesson and on the homework, you're going to be able to know what to do with it and what the meaning is. Let's test our skills on another problem. I'll read the problem and then I'm going to pause the recording as students work on it in class. Vanessa is mixing formula for her baby, and the graph given to the right describes the relationship between the ounces of water to the scoops of formula to make a properly mixed bottle. Does this graph describe a proportional relationship? Make sure you justify your answer. What's the unit rate? Where can I see it on the graph? At a different location on the graph, show and explain how you can find that same rate or ratio, and then write an equation. Use that equation to answer the question that follows. So I'm going to pause the recording as students work on this in class. You pause the recording as well as you work on it, and then we'll come back together to go over it. Pause the recording now. All right, let's discuss part A. Does this graph describe a proportional relationship? What do you think? Emily? Great. We are looking for crosshair points, and we're seeing that these crosshair points allow us to count the slope. And I can see that I'm going up 3 and over 1 every time. Yeah. Who else has another justification? Tanner? Exactly, it's a straight line that goes through the origin. The straight line part happens because I've got this constant slope, as Emily described. That's what makes it a straight line. If I'm always going up 3 and over 1, that's what creates that linear relationship. So, straight line that goes through the origin, consistent slope, those are great justifications. What is the unit rate for this relationship, and where am I going to see that on the graph? Okay, Gabe, go ahead. Exactly, 1 scoop for every 3 ounces. I love finding a unit rate on the graph because it means all I have to do is go over on the x-axis to find the 1, and once I've gone over and found that 1, I just follow it up until I reach the graph, find out that that value associated with it is 3, so that's 3 ounces, and I love that you made it quantitative and gave those labels, 3 ounces for every 1 scoop. Let's put a star on the unit rate, just to show that we found on the graph. At a different location on the graph, explain how you can still find that unit rate. So we can't use the star anymore. That was the easy one. Where else can we see the unit rate? Okay, Oren. Yeah, 2 scoops and 6 ounces. So I'm going to go over to 2 scoops and 6 ounces, choosing that point there. How am I actually seeing that? Well, because 6 ounces and 2 scoops can still simplify, because these are equivalent ratios in a proportional relationship, to 3 ounces and 1 scoop. Can you then write an equation? We don't have a table this time to help us out, but we can see some really nice patterns. What is that equation going to be? Okay, check in at your tables one last time. I want to see some hands. What is that equation going to be? And if you're stuck, then make a table. We've got some values that we can put in the table. Then we can start looking for how the x changes to a y. Get ready to do that, and then also answer question E when we return from the pause break. Check in with your tables one last time. Pausing the recording now. All right, who can share their equation with me now after that pause break? Okay, let's go Grant. Say that again. Not a third of x equals y. I know that you're recognizing this really important relationship, but we want to talk about how we're going forward. So let's figure out where you got that information and see how we can fix that misconception. When the x value is 1, what's the y value? 3. When the x value is 2, what's the y value? 6. X value of 3, y value is 9. How is an x changing to a y? How is that 3 changing to a 9, a 2 changing to an x, and 1 changing to a 3? Esther? We're multiplying by 3. So what happens if I have an x value, a mystery number x value? What am I going to do to go across the table? Still going to multiply it by 3. And when I do, that's how I get the mystery y value. X times not 1/3, because if I multiply it by 1/3, 1 times 1/3 isn't 3. So you do recognize that relationship, that 1/3 of the amount of water is how many scoops, but how we write that down in equation form is a little bit different. So the x changes by multiplying by 3 to become a y. X times 3 equals y, or we can write y equals 3x. Okay, and how many scoops of formula must Vanessa use to make a 9-ounce bottle for her baby? We can answer this question in a lot of ways. Let's start with the graph first. 9 ounces of water. How many scoops is that going to be? That's 3. How can I also use the equation? Y equals 3x. What value do I know? The y value. This is the y value. So that means, since I know the y value, I substitute it in. 9 is equal to 3x. We undo multiplying by 3 by dividing by 3. And algebraically now we can get the same answer that we got on our graph. X is equal to 3, or 3 scoops. All right, let's finish up. Ben, Boston, and Brighton have each designed a remote control monster truck. They line them up to crush some mini cars in the driveway. The lines on the graph below show the distance in inches that each monster truck travels in time in seconds. Brighton states that each truck is traveling at a constant rate. Is this statement correct? Why or why not? Talk at your tables. We're not going to pause. We're just going to talk at our tables and be ready to discuss in about 20 seconds. Ready, set, go. Do you agree with Brighton? Are each of the trucks traveling at a constant rate? Tanner? Exactly, it's just that simple. They're all straight lines that go through the origin. A constant rate also means that they have a constant slope. That's what makes them straight lines. So let's look at Ben. And for Ben, it's going 4 inches in 1 second, which means 1 second later after that, it's going to go another 4 inches. That's what we're talking about with, are they traveling at a constant rate? And we can look at Brighton. I can see that we're going over 3 and up 4. So I can also pick another spot on the graph and go over 3 and up 4 and still land on that same line. So yes, they are traveling at a constant rate. They're straight lines, and they're straight lines that go through the origin. So that means they have that constant rate. But I want to focus on the part that the constant rate part happens because of that slope. What do the values in the ordered pairs given on the graph represent? I already talked about this point here. This 1, 4, what does that 1, 4 represent? That's 4 inches every 1 second. Your turn now. What does it mean here for Brighton? What does the 6, 8 mean? And for Boston, what does the 4, 2 represent? With your tables. Ready, set, go. Okay, what does Brighton 6, 8 mean? Brighton 6, 8. Esther. Great, 8 inches in 6 seconds. And Boston, what does Boston's 4, 2 represent? Emily. Two inches in 4 seconds? You're close. You're really close. Let's take a look. This is the X value. And what is the X value measuring? The time. The 2 is the Y value, which is measuring the distance. So what changes do I need to make? None. Sorry, I was mistaken that time. You did great, Emily. Like I said, I'm pre-coffee. Did not get sleep last night. Did I scare you, Emily? I scared myself too. Okay. Next question, find the unit rate. We've already done the first one. It was given to us as a unit rate. Ben is going 4 inches every second. We need to turn the rest of these into a unit rate. Let's review what that looks like. I need the value to be a 1. I want to know how many inches are they going in 1 second. So how does a 6 change to a 1? Divide by 6. What am I going to do with the 8 then? Divide it by 6. We're treating these as these equivalent ratios. So I'm giving them the same treatment to the top and the bottom of that ratio. And I heard 4/3 of an inch. Great. And what am I going to do here? 2 inches in 4 seconds, but we need to turn it into a unit rate, so I want that to be a 1 second. How is that 4? Going to change to a 1. Divide by 4, 2. Getting the same treatment, 2 is also divided by 4, keeping this ratio equivalent. And I get 1/2 of an inch in a second. Who is traveling the fastest? We can answer this question in a variety of ways. Will you check in with your tables? All right, and back to me. Which truck is moving the fastest, and how did you answer that? How did you tell? Leroya? Yeah. So did you use the unit rates for that? Yeah. Great. So when we find the unit rate, it's very easy to compare. 1 second across the board, who's going more in that 1 second? Obviously it's Ben. That's why we like that unit rate. Who could have answered this question without finding the unit rate? What if I just presented just this information and said who's going the fastest? Could you answer that question? Okay, how can you answer that question, Tanner? Yeah, looking at the slope. Ben has the steepest slope. Higher unit rate, steeper slope. Okay, explain why the graph of a proportional relationship makes a straight line. I think I've mentioned that enough times throughout all of here. Why do we have a straight line? Because that slope is constant. That's those equivalent ratios. That slope is constant. And part of your homework, I want you to summarize what you know about proportional relationships. What are all the things that you know? We've very recently reviewed it. Write down at least 3 things that you know about proportional relationships. In addition to finishing up question 7, summarizing what you know about proportional relationships, I do want you to complete the homework section. That's it for watching, or that's it for today. Thanks for watching. We'll see you next time.